Let R be any ring, and we'll use R mod to denote the category of R modules. Recall that an R module consists of firstly an underlying abelian group M, and its group operation is usually denoted by addition, and secondly an action of R on M. i.e. well, this is not a group action, it's a ring action, i.e. function R cross M to M, where this is an abelian group homomorphism. You can think of R cross M as an abelian group, and this is a function which we usually denote by R comma M goes to Rm, and it must have the property that R dot S dot M, so if I use dot here, is Rs, where this is multiplication in R dot M, so a sort of associativity property. Okay, so these two pieces of data give you an R module, and the category of R modules consists of its objects are all R modules, and its arrows, so given to R modules are M and N, an R module homomorphism from M to N is a function such that well, it's actually a group homomorphism of abelian groups M to N, such that f of Rm is Rfm for every R in R and for every M in M. So basically it respects the actions of R on M and M. And so the category of R modules has as its arrows R module homomorphisms. Now there's a functor omega, the forgetful functor, which I'll denote omega from the category of R modules to the category of abelian groups. So this category of abelian groups is the category whose objects are abelian groups and arrows are group homomorphisms. And what this functor does is that given an R module M, omega M is just the underlying abelian group. So it's called forgetful because you're going to forget this second part of the data defining an R module, namely the action of R on M. And given an R module homomorphism, well, we defined an R module homomorphism to be firstly a group homomorphism, and then it must have this additional property that f of Rm is equal to Rfm. So an R module homomorphism is an abelian group homomorphism, so we'll just write f itself viewed as a group homomorphism. So that's the forgetful functor. And the question that we shall address now is, what are the natural transformations eta from omega to omega? Okay, so this this collection of natural transformations we can denote by nat omega omega. So we are asking what is nat omega omega, and sometimes this nat omega omega is also denoted by end omega, which means the endomorphisms of the functor omega. That's just terminology. Now note that end omega is actually a monoid because firstly we have the identity natural transformation from omega to omega, and secondly if you have two natural transformations, eta from omega to omega and mu from omega to omega, then we can get mu circle eta is also a natural transformation from omega to omega. And you can show that this composition law will satisfy the axioms for being a monoid. So the question is, can we describe this monoid endomorphisms of omega? You can try to solve this yourself. Pause the video now and try to see what to do. It's a bit tricky, so you may need to look at the solution that I'm going to provide. So we want to compute end omega. Now I claim that end omega is the same as R. In fact, end omega is not just a monoid, but is actually a ring. The monoid structure will be the multiplication structure on this ring, and there will be an additive structure. But firstly, let's just see how this works at the level of sets. So, so suppose you have a natural transformation from omega to omega. And now the first hint as to how to solve this problem. Now, R itself is an R module. R acts on itself by left multiplication. And so what we have is eta R from R to R. So this should be an R module homomorphism. No, not an R module homomorphism, a homomorphism of abelian groups, because well, eta R should be from omega R to omega R. A homomorphism of groups. Now in this R we have an element 1, and let A equal to eta R of 1. And what I want to say is that we will see that eta is completely determined by A. So what will happen is that to each natural transformation we will be able to associate an element A of R. Well, this belongs to omega R, but as a set that's the same as R. Okay, so let's see this. So suppose M is any R module. Can we figure out what eta subscript M is based on the fact that eta R of 1 is A? So, so let's try to figure out what eta M of little m is. So, and let M be any element of M. We want to figure out what is eta M of little m. So for this, what we'll do is let phi subscript M from R to M denote the R module homomorphism which takes R to R times M. You can check that this is actually an R module homomorphism. And now let's apply naturality to this phi m. So naturality of eta means that the diagram involving eta r and eta m. So we have omega r to omega r. We have here eta r. And then we have omega r to omega m, which is omega phi m, which is just phi m as a function. And here we have omega r to omega r. And this is also omega phi m. This is omega r to omega m. This is also omega phi m. So this is again phi m as a function. And here we have eta m. And naturality means that this diagram commutes. So we signify commutes by drawing a circular arrow like this. What does commuting of this diagram mean? That means that eta m circle omega phi m is omega phi m circle eta r. Now let's see if we can evaluate eta m of m. Well, eta m of m is eta m of phi m of 1 is going to be m. Let's recall the definition of phi m. Phi m of r is r times m. So phi m of 1 is just m. So this is eta m phi m of 1. But that is the same as eta circle omega phi m. And that's the same as by the commutativity of this diagram, that's omega phi m circle eta r. Of 1. And so that's omega phi m circle eta r of 1, which is phi m of eta r of 1, which is a, which is am. So what we see is that eta m is completely determined by this element a of r and the fact that eta is a natural transformation. So each natural transformation from omega to omega gives rise to an element of r. Can we do the reverse? So what we have constructed is from nat omega omega to r, and eta goes to eta r1. So this is what we have, a function from endomorphisms of omega to r taking the natural transformation eta to eta r of 1. Now let's try to construct the inverse of this. So conversely, given a in r, define eta from omega to omega by setting eta m of m is equal to am. Okay, we'll call this eta superscript a. So this is the eta associated to a natural transformation associated to a. Is this a natural transformation? Actually, we need to check that. So given any R module homomorphism, we need to check that this is a natural transformation. So we need to check if the diagram omega m to omega n, here we put, this should be an n, omega f, and then we have omega m to omega n, okay, this is not how I want to do it. I want to say omega m to omega m, and here I'll put eta subscript m. Here I'll put omega f, and here I'll put eta subscript n. So this will go to omega n, and here we have omega f. And we want to know if this diagram commutes. So we want to know if eta n circle, so this is eta a n, circle omega f of m, whether this is equal to omega f circle eta m a of n. So let's evaluate this thing. So this is a of f of m, right, by definition, because omega f is just f as a function, and then this eta n a just multiplies it by a. But because f is an R module homomorphism, this is f of am, because f is an R module homomorphism. And so this is omega f circle eta a m of m. So we have that indeed this diagram does commute. So we've constructed a bijection clearly eta a of r subscript r of 1 is a just by definition. So this is the inverse of eta goes to a. So we have a bijection from end omega to r given by eta goes to eta r1. And we can also check that so this end omega has the structure of a ring, not just a monoid. How is addition given? Given eta mu belonging to end omega, you can talk about eta plus mu. Eta m plus mu m for every m. You can check that this will also be a natural transformation, and you can define eta composed with mu of m to be eta m circle mu m. And so this has the structure of a ring. R also has the structure of a ring, and this map is actually an isomorphism of rings. So let's call this phi. Phi is actually a ring isomorphism of rings. The main thing to check is that if you take eta superscript a circle eta superscript b, then this thing at 1 is eta a of b, which is ab, which is the same as eta superscript ab r of 1. Therefore, eta a circle eta b is eta ab, because this value completely determines the composition. So because they agree on R at 1, they must be equal. And so finally what we have is the following theorem. and omega is isomorphic to R as a ring. Now this is a remarkable observation, because what it says is that, okay, you just start with the category of R modules, and from that category you can recover the ring R itself. So in some sense it is saying that the ring comes from the category. So if two categories of R modules are actually isomorphic, then the underlying rings are also isomorphic. Let's look at a variant of the previous problem. Earlier we had the forgetful functor from R modules to R modules. Now let's consider the identity functor from R modules to R modules. So this is the functor which takes each R module to itself, and each arrow of R modules, that is each R module homomorphism, also to itself. And now the question is, what is end of this identity functor? Now we can proceed as before. We have an R module R. So given eta in end identity R, we have eta R. Now earlier this eta R was from omega R to omega R, but this time it's an R module homomorphism from R to R. And now let A equal to eta R of 1. Now, but as before, we will see that A completely determines eta R. Why is that? Well, just as before, given any M R module M and any element M in M, consider the R module homomorphism phi M from R to M given by phi M of R equals Rm. And now we have this commutative diagram: R to R, eta R, R to M, phi M, R to M, phi M, and M to M, eta M. This commutes, which means that eta M of M is eta M of phi M of 1, which is phi M of eta R of 1 by commutativity, which is phi M of A, which is AM. So as before, we see that eta is completely determined by this element A. So phi eta M of M is AM for every element M of every R module capital M. Okay, so now let's but what changes this time is that not every element A of R gives rise to a natural transformation. So the key issue here is that so what we have is that for every A in R, we have eta AM must take M to AM. We can try to define this, but is this a natural transformation? Is this a well-defined natural transformation? So I'm just trying this out, okay? And so let's just try it out on R. So we have eta R of R. Well, on the other hand, on one hand, this is going to be just AR by this calculation here. Eta M of M is AM, so I'm just applying R here. But on the other hand, this needs to be an R module homomorphism. So this should be eta AR, I can write this as R times 1. But that is by definition, because it's an R module homomorphism, this is R times eta A, R of 1, but that is R times A. So eta RA is an R module, eta RA is an R module homomorphism if and only if RA equals AR for every R in R. In other words, if and only if A belongs to the center of R. That's just by definition the set of all R in R such that RA equals AR, the center of the ring R. It's easy to show that if A is indeed in the center of R, then eta A is an endomorphism of the identity functor. And so the conclusion is that end of the identity functor of R is the center of R.